Hello and welcome to our lesson on inverses of exponentials and logs. So at the end of the last topic we talked about log functions, and what we basically figured was that if we had something like y equals 3 to the x power, if we were to rewrite that in its equivalent log form, that we would have x equal to, remember the exponent is the answer, the log base 3 of y. But if we were to switch the x and the y and make it y equals the log base 3 of x, that these two functions, and we saw this graphically, ended up being inverse functions. So we said that logs, or basically what this boils down to, is that logs and exponentials are inverses. So we're going to spend a little more time in this particular topic finding the inverse of a log function and finding the inverse of an exponential function. And sometimes it's as simple as rewriting, but just so you can we can refresh on the steps for finding an inverse. Okay, let's look at a linear function. Those are the easiest ones for us to deal with. Let's say our function was y equals 2x plus 1. Now I know the inverse function has to have the opposite operations, so a minus 1 and a divide 2, and in order to make sure those operations were undone in the correct order, we said let's just solve this for x. So if I was to solve this for x, I would subtract 1, and that would give me y minus 1 equal to 2x, and then I would divide both sides by 2. So once x was alone and equal to y minus 1 divided by 2, that's technically has the inverse operations, but technically, okay, this function y equals 2x plus 1 and this function, these are the same function, they're just rearranged. And let me just show you. If I was to graph y equals 2x plus 1, and if I was to graph x equals y minus 1, sorry, I'm so slow, all divided by 2, it is the same function. That red one went right on top of that blue one. Those are the same function. They're just rearranged, okay? In order to actually make this the inverse, we had to flip-flop the x's and the y's. So if I put y equals the x minus 1, I swear I hit x. No, I hit the times, oh my gosh. X minus 1 divided by 2. That's not what I wanted. Geez, if I actually flip-flop, if my fingers could type here, flip-flop those, then I would get the inverse function. I would get the reflection over the y equals x line there. So we want to solve for x, but then we have to flip-flop the x's and the y's to actually capture that inverse. So when we switch the x and the y's, when we switch them and make this x minus 1 over 2 equal to y, we actually have the inverse, and then we just use our little inverse notation to call it the inverse. So that's the concept. Okay, we're going to solve for x, flip-flop the x and the y's to actually get the inverse, and then use our inverse notation. It's just that solving for x, when we're dealing with exponentials and logs, revolves one or the other. If we're going to solve for x when it's exponential, we'll use a log. If we're going to solve for x when it's in log form, we'll use our exponentials. Okay? So again, just to recap those steps. Solve for x. We switch x and y. And then we use the correct notation to capture all of that essence. Okay? So let's look at this when we're dealing with logs and exponentials. So the inverse, it is important to kind of put in the memory bank, the inverse of an exponential is a log. Even though I can take an exponential and put it in an equivalent log form, the inverse of an exponential is also a log. So they can be linked as equivalents, but they can also be used as inverses. Okay? So the inverse of an exponential is a log. So if I want to find the inverse of an exponential function, I'm going to rewrite it in log form. And then if necessary, I may have to do a little bit of solving to get x all by itself. And then it should be that those x's and y's are switched. So we want to make sure that we write with correct inverse notations. Remember y with the little negative 1 here, that's y inverse of x. That's our correct notation. Okay, so let's look at how this is going to work here. Now we should technically already know the inverse for this because we talked about it at the end of the log functions, but if I wanted to solve this for x, Okay, if I wanted to solve this for x, then rewriting it in log form is going to do that. So x would equal the log base 3 of y. Okay, so solving for x, there it is. Okay, x is all by itself and it's equal to log base 3 of y. So after I solve it for x, x is already by itself. I forgot to put in here a step. So we have to switch x and y. And then write with correct inverse notation. Okay, so here we solved it for x. X is all by itself, so we're good there. Now I have to switch x and y, so y equals the log base 3 of x, and then we're going to call it the inverse. Y inverse is equal to log base 3 of x. Now, that's a few extra steps from what I showed you at the end of the log functions notes, but sometimes there's a little more going on in the function, and the process is helpful. So this is our inverse. If you were to graph these two functions, what you would see is one is a reflection over the line y equals x. Everything would be switched. Domain and range would be switched. X and y intercepts would be switched. Horizontal and vertical asymptotes would be switched. Okay, everything would be switched. All right, so let's look at this one. If we wanted to solve this one for x, we would again rewrite this in log form. So our exponent's going to be our answer. X plus 1 is going to equal the log base y of 2. Sorry. Log base 2 of y. So remember, the exponent is the answer. The base is the base. Okay? So here it is. But this one, we're not done solving for x. So when I want to solve for x, I put it in log form, but x isn't by itself on this one. So notice there's a plus 1 here I have to get rid of. So I want to subtract 1 from both sides. So then x is going to equal the log base 2 of y. And I want to make sure that minus 1 is after the function, and it's not with the y, that it's a shift down and not a shift to the right. Okay, so I'm going to keep that log base 2 of y in parentheses. Now, x is by itself, so this is my inverse function. I just have to flip-flop the x and the y. So y is going to equal log base 2 of x minus 1, and then call it the inverse. So y inverse is equal to log base 2 of x minus 1. And there it is. Okay? So that's our inverse function. Let's try this again. Actually, it's a spot for you to try if you're feeling confident with this idea. Then give it a shot. So if I want to solve this for x, I'm going to rewrite it. It becomes 2x equals, the exponent's the answer, the log base 5 of y. We're trying to solve for x here. It's being multiplied by 2, so I want to next divide both sides by 2. So that x is going to equal, I could leave this log base 5 y divided by 2, but that's the same as 1/2 times the log base 5 of y. So dividing by 2 or multiplying by 1/2 or bringing the half out in front. Either way, I think you're more likely to see it in this form, but then you're done here. Okay, x is all by itself, and so once we've solved for x, we switch x and y. Y equals 1/2 log base 5 of x, and then we're going to call it the inverse. So y inverse equals 1/2 log base 5 of x. And that just got a little bit squishy. So there we are. That is our inverse function. Okay? Now the next one, we have a base of e, which we haven't encountered in a while. When we are rewriting with the base of e, remember we want to use natural logs. So if I was rewriting this one, it's going to be exponent is our answer, so x equals, we're going to go with the natural log base e of y. And again, we use natural log because it's already base e, so this is the same thing as just saying natural log of y. Now, x is solved for. We've solved for x. X is all by itself, so we're done. We just need to switch x and y. So y equals the natural log of x, and then call it the inverse. So y inverse equals natural log of x. So the natural log of x and e to the x are inverse functions. Okay? Similarly here, we would make this exponent the answer, so x minus 2 equals the natural log base e of y. So again, this is the same thing as x minus 2 equals just the natural log of y. Now we rewrote this so that we can try to solve for x. X isn't by itself, however, so we need to add 2 to both sides. So x is going to equal the natural log of y plus 2. So now that we've solved for x, we can switch x and y. So y equals the natural log of y. Actually switch them, how about that? The natural log of x plus 2, and then we're going to call it the inverse. So y inverse equals the natural log natural log x plus 2. And that is that. Again, if you graph this original function, this original exponential, and this new log function, you're going to see all the properties of x's and y's are flip-flopped. Okay? Alright, if you're feeling good about this and you want to pause and give it a shot, go ahead. Otherwise, we're going to solve for x here. Now, this one's a little tricky because if I go to rewrite this, what happens with the 3 is interesting. So what I would do here is, so remember we have an argument, we've got a base, we have an exponent, but there's nothing in the rewriting process that accounts for that multiplied by 3. So what I would do, just like if I was solving a normal exponential equation here, is I would get rid of that times 3 by dividing both sides by 3 so that I don't have to account for it in the rewrite. So y divided by 3 is equal to e to the x power. Now if I want to solve for x at this point, I can rewrite. So I'm going to say x equals the natural log base x of y divided by 3. And there it is, right? Exponent's the answer, base is... What am I, guys? I'm freaking losing it. I'm so sorry. I'm like trying to talk and I don't know what's happening in my head right now. So let me just do this again. Divide the 3 over. Now we're ready to rewrite this. So the exponent of x becomes the answer. It's going to be equal to the natural log, which is already base e, of the argument going to be y over 3. So now we are solved for x. But remember, that base of e, that's implied there. So I'm writing it just so you don't see, or so you see it doesn't just disappear, but this is the same as just the natural log of y over 3. But we have solved for x. X is alone. So now I'm going to switch x and y. So y equals the natural log of x over 3, and then we're done. We just need to call this the inverse. So y inverse is the natural log of x over 3. Okay? So we're trying to solve for x, which involves rewriting. Sometimes we're done. We may have to add or divide. Switch x and y, call it the inverse. Same steps we looked at before, it's just a little weird because we're not used to these exponentials and logs. Now we're going to try this in reverse. In the same way, the inverse of an exponential is a log. The inverse of a log is an exponential. So the inverse of a log is an exponential. So if we're going to try to find the inverse of a log function, then we're going to rewrite in exponential form. But we want to get that log piece alone. Again, when we go to rewrite, if there's extra stuff, it's not going to have a spot. So like this times 2, there's no place in the rewriting process for that times 2. So if necessary, we might have to get the log part by itself and then rewrite in exponential form and solve for x again if we need to. We're rewriting to solve for x, that's the whole purpose there. And then I just want to switch, again I don't know why I didn't put the step in here, switch x and y, and then we're going to write with our correct notation. Okay, so let's try this out here. If I wanted to solve this one for x, I'm going to rewrite my log in exponential form. So in exponential form, this would be 4 to the x power, just kidding, 4 to the y power equals x. The base is the base, and the exponent here is the answer here. So it's 4 to the y power equals x. So I've solved it for x. That is rewriting solves it for x. So when we're looking at y equals x plus 1 and I say solve for x, we minus 1, right? If I want to solve for x when it's a log, I use an exponential and vice versa. So I solved it for x by rewriting. So now I need to switch x and y. So 4 to the x power equals y, and then call it the inverse. So 4 to the x equals y inverse. So these are opposite functions, log base 4 and 4 to the x power. And that's what we saw at the end of our log functions notes. I just want to give you the process here because sometimes there's a little more to it. For example, in this next one, there isn't a place in the rewriting for that times 2, so I'm going to divide both sides by 2. So we have y over 2 equal to the log base 3 of x. So now when I rewrite this, it's going to be 3 to the y over 2 power equal to x. So I'm done. I've solved this for x. This is technically my inverse operations. I just need to switch x and y to make it the inverse function. So x over 2 equals y, and then I need to call it the inverse. So 3 to the x over 2 power equals y inverse. Done. Okay? Same thing here. If you're feeling like you can do this, give it a shot. We're going to try to solve this for x by rewriting it. So this would be 8 to the y power. That's ugly. Try that again. 8 to the y power equal to x plus 1. So the exponent's the answer, base is the base, right? So now if I want to solve for x, there's going to be an extra step here because x isn't by itself. Sometimes rewriting is enough to solve, sometimes we still have to solve. So we have 8 to the y power, then we have a minus 1 equal to x is now by itself. Now that it's solved for, we switch x and y. So 8 to the x power minus 1 equals y. And now we're going to call it the inverse. 8 to the x minus 1 equals y inverse. And again, everything's going to be switched on these. So let me show you. Just you want to use this as a way to verify your work. If we were to graph y equals the log base 8 of x plus 1, there's our function. Now let's graph y equals 8 raised to the x power, and then afterward a minus 1, and then we see it. There is a reflection of our two graphs where everything's the opposite. And if you want to just verify in the graph that it's a reflection, let's type y equals x in there. That's our parent linear function. That's the reflection line. If everything looks symmetric about that line, you have the inverse function. Okay? So you can verify what you're doing graphically. All right, natural log we know is base e. So even though we don't see it, we know there's a base e here. So if we go to rewrite this, this would be e to the y power equals x. Okay, x is solved for, so all we have to do is switch these. E to the x power equals y is our inverse. So e to the x equals y inverse. And this is the same problem we had on the front. Okay, our natural log of x and e to the x are going to be inverse functions. Here, again, this is a base of e. So this becomes e to the y power equal to 2x. Now 2x, we have to do an extra step here. X needs to be alone, not 2x. So we're going to divide both sides by 2, canceling that out. So we're going to have x equal to, I can leave it as e to the y divided by 2, but you're more likely to see 1/2 e to the y power. That way you can see it as a compression of the graph, right? But in either case, x is solved for. So we just need to switch x and y, and then call this the inverse. So e to the x power equals y's inverse. And that is that guy. All right, one last one. Again, if you want to give this a shot, feel free. Otherwise, before I rewrite this, that plus 3 doesn't have a place to go. So I'm going to start by subtracting 3 from both sides. So we have y minus 3 equal to the natural log of x. And then remember, this is base e. So when I rewrite this, to solve for x, it's going to be e to the y minus 3 power equal to x. Done. Solved for x. The rewriting solves for x. So we just need to switch x and y, and then call it the inverse. So e to the x minus 3 equals y inverse. And there it is. Okay, so same steps we've talked about before, where you solve for x, switch x and y, call it the inverse. It's just that that solving for x piece is weird, okay? The solving for x, it requires a log if it's in exponential form, it requires an exponential if it's in log form. Okay, so that's the piece you got to try to wrap around your brain, but you can verify graphically that you've got the correct inverse function because you should see a reflection. And yeah, you should have enough to get going, and that really wraps up our unit, our module for exponentials and logs. So, as always, if you need some extra help, reach out. I'm here to help. And yeah, I think that's good. So you have enough to get going on your quiz. So just email if you need some extra help. Otherwise, just yeah, I'll talk to you soon. Take care.